As you're probably able to tell from what's written behind me, is we're going to start talking about the Sn1 E1 pathway, and we're kind of on this steadily widening path that makes things harder and harder for us to understand. So as always, I'll kind of talk about the way that I understand these processes, and kind of what you should depend on is as you get more experience and more homework and you kind of are exposed to more and more of this world, it becomes a little bit easier to kind of dial in which one of these pathways, whether it be E2, Sn2, Sn1 or E1, actually occur. And quite honestly, usually it's not hard to tell when the Sn1 E1 pathway occurs relative to the E2 Sn2 one, but the one that is often going to be difficult is kind of to differentiate between like product distributions between each one of those separate pathways, the E's and the S's. And so the one thing that I can really say about this is now that we're in this Sn1 E1 world, honestly, pretty much if there's any chance that a substitution or an elimination would occur through this pathway, pretty much both of them are going to happen. Like you'll read a lot of things on the internets that indicate that, oh, this is going to be the primary product always, and this is going to be the primary product always. But it's been my experience actually doing these things is that once you're like in this you're in this unimolecular type pathway here, pretty much anything happens, and you might be able to kind of like push on the gas pedal for one product relative to another a little bit, but honestly, you're going to end up with mixtures. And so that's kind of the way I'm going to teach it. So the first thing we're going to do is I'll just write down kind of a quick summary of the stuff that we've already talked about, which is the Sn2 E2 world. And then I'll try to delineate some really major differences now that we're in this unimolecular world. So here are those major mechanistic differences between the Sn2 and the E2. Keep in mind that this thing depended on the ability of a nucleophile to approach the backside of an atom, usually carbon, and give it a good punch so that the leaving group pops out the other side, and that would lead to a substitution product, hence the S. Then the E2 reaction, and even though I've represented this as a nucleophile, we now know that that's really more of a, kind of understood more as a base, and the base reaches in, rips off an H in an antiparaplanar fashion, and in kind of a similar way punches the leaving group off through a couple of extra arrows, and we end up with an elimination product. The one thing that was kind of common between these two different pathways was the fact that they were bimolecular in terms of their rate, which means that when we looked at the potential energy surface, you only had that single hump with a single transition state. I'm going to just summarize that on the board here, and then we'll go and look at why the E1 Sn1 is so different. So hopefully this isn't too hard to read, especially since it's just a review. So for both of these reactions, keep in mind the rate of both of them is proportional to both the concentration of nucleophile and the concentration of substrate. And we talked about important considerations in both of these, along with solvent. We also saw a potential energy surface that had that single hump, right? And so the faster reactions were the ones with a much smaller hill. So that's kind of one of the ways we described, why why it might matter what the nucleophile looks like and what the substrate looks like in terms of the height of that hill. So let's actually take a look at the mechanisms for an Sn1 specifically, and just contrast that with the mechanism for the Sn2, and we'll do the same for the E's. Okay, so what's different about the Sn1? Well, for one, you might suspect already that one is telling you something about the rate equation, and you'd be right. It turns out that the rate of these things is wholly dependent on the concentration of the substrate. The nucleophile doesn't matter. And so there are different reasons for that, which we'll certainly talk about, but let's write down for an Sn1, the rate is proportional to only the concentration of whatever that substrate happens to be. Really, the reason for that is you're going to observe Sn1s and also E1s when you don't really have a very good nucleophile, right? If you think back to when we were first talking about considerations in the nucleophile and we said we were going to look for something with a minus charge or alt nitrogen, what's missing in just about every Sn1 and E1 in the entire universe is that is it has a nucleophile that's not really strong enough to actually give that punch that's necessary to get the Sn2 or E2 to occur. So what we instead are basically doing is we're going to be standing here kind of waiting around for the substrate to just fall apart spontaneously, right? And that takes a little bit longer usually. So the way that we can kind of think about this thing, and we'll see specific examples of the mechanism in just a second, one of the major differences in terms of the step that happens here is that the slow step is really the step where we're just kind of tapping our feet saying, come on, would you please react? And we get this kind of arrow, right? You'll notice that there is nothing pushing that leaving group off. And what we end up with is this truly electrophilic species. If this was a carbon, that would be the dreaded carbocation, which we talked about a whole bunch first term. In which case, that means that if this thing truly does have this intermediate that's just kind of hanging around waiting to react, you open yourselves for rearrangements, either hydride shifts, alkyl shifts, ring openings, ring closings, all that other crap. All that other stuff. We'll try to be a little bit more professional here. So those same kind of problems are going to be with this kind of intermediate. And then, of course, in a subsequent step, there'll be some sort of nucleophile. Remember, a very, very weak nucleophile that now has the chance, because it's so weak, well, even a weak thing is going to want to interact with that super electrophilic species. And then through what usually takes a couple of steps, you're going to get your substitution product. Right? And so what you'll notice here, the big difference is that you have this intermediate, right? And that's one of the most important things in terms of recognizing that unimolecular processes like this usually have, when you look at the potential energy surface, yeah, it looks like you can still see that. What you have is this kind of double hump phenomenon. Right? You've got this big initial hill, you've got this little part right here that is the intermediate, and then you've got your product formation that's usually not rate limiting, so it's usually just a little blip along the way. So it turns out that this site right here, this intermediate, is really this E plus species, right? So really, we're going to most often be thinking about this as some sort of carbocation. And then, of course, once you get to that high potential energy state, that's where you could potentially get hydride shifts, alkyl shifts, and all that other crap I talked about. Or you could simply get the normal Sn2 type reaction where it just directly reacts with that weak nucleophile, and there's a couple other like little mini humps out here. But that's really the major difference. And quite honestly, even though I'm picking on the Sn1, it turns out the E1 happens in a really particular fashion, or very similar fashion as well. You still go through the exact same intermediate. The difference is that if we go on the E1 pathway, that's going to involve some sort of further reaction with the nucleophile, where let's say there's some H out here, whatever else. And that nucleophile will reach in and do that kind of elimination product, right? And so one of the reasons that when I first introduced this E1 Sn1, I said that there's kind of like not really any good way to select between exclusive products, but it's kind of like a mix of a whole bunch of other a whole bunch of products, is because, right, that high energy potential energy intermediate can really go in a whole bunch of different directions, right? And in fact, energetically, the hard part is just getting that to happen. And once it has, it's just kind of like, woohoo, open the floodgates, all kinds of crazy stuff can happen. So even though we'll talk about kind of ways to, in a future video lecture, probably not this one, ways to kind of increase your amount of substitution product and increase your amount of elimination product, really they're both going to occur together regardless of what the internets might say. So let's kind of do a similar thing here, considering some different factors that are going to influence whether what pathway you're in. The first one I would say is probably the most important, is that this kind of pathway is only really important when there's no good nucleophile, right? So we'll just say if Nu has, that's a little confusingly written there. So if the nucleophile has no negative formal charge or is not a nitrogen, or we'll just say in N family, the pnictogen family, then this pathway is likely. And one of the super unsatisfying things about the way I've kind of named this is that it's kind of a measure of the reality we live in, where I kind of have to qualify everything and kind of not make like really bold statements. But you know, in general, right, like 95% of the time, you're only going to consider this pathway if there's no minus charge in your nucleophile that you've identified, or if that thing is not in the nitrogen family, then we're going to consider this pathway. There's of course a bunch of other considerations, but that's kind of the major one that I ask. So in my mind, I kind of have like Sn2 E2 land over here, and I've got Sn1 E1 land over here, if you can see my hand. And the real question that I always ask is this, right? What pathway am I going to choose to start off with? And of course, we'll develop this more in a future video lecture. So other things to consider. Well, it turns out that many of the things that we considered back in the Sn2 consideration chapter still apply here. So let's kind of go through a couple of those. One of them is that the best leaving groups, right? In other words, the leaving groups that you're going to just like sit there and wait around for, the ones that are more likely to actually show some sort of reaction, are the weakest bases, or worst bases, right? And so that's actually a similar, it's actually a similar concept between the two pathways. So things like tosylate, right? The thing that we talked about as being a really weak base, and this like a really spectacular leaving group, is going to be a really spectacular leaving group in E1 Sn1. In other words, it'll increase the reaction rate. Maybe I'll step away and I'll include like a little resource guide or a little picture right here that kind of shows you some of those patterns. And so, you know, we're still going to kind of consider the substrate, but and that considerations happens to be the same. But the one thing that's going to change in a major way, and I'll have an example of this, is that now, before we used to see that reactivity pattern with Sn2s that said, well, you know, we have primary is much more reactive than a secondary, which is much more reactive than a tertiary. Well, in a typical organic chemistry class, usually I teach you one thing and then completely reverse all that logic in the very next mechanistic pathway, and that's what's happening now. And so it turns out that tertiary substrates are far more likely to enter Sn1 E1 pathway. And assuming that I have any space there, I'll step away for just a second and I'll include like a screenshot of a graphic that really kind of helps me to think about this. And on there, you'll see there's a huge difference between tertiaries, secondaries, and primaries, right? Tertiaries are orders of magnitude more likely to undergo this Sn1 E1 pathway. If you're waiting, for instance, for a substrate that is primary to undergo an E1 Sn1 pathway, you're going to be waiting for a hell of a long time, and which means that really isn't going to be a very likely reaction, unless that's the only reaction that can occur, but it's going to be god-awful slow, right? Ugh, man. So let's take a look at a couple of examples. So some jerk someday sets this thing up where this is a tertiary substrate. It's got a really good leaving group, and then you look over the reactants and you say, is there anything with a minus charge or in the nitrogen family? And you would say no, right? This is a perfect example of something that is definitely going to undergo like an Sn1 E1 type pathway. You'll notice that I made this like a pretty simple system, right? I didn't put a lot of spinach out here because that spinach drastically complicates your product distribution, which is something I think a future homework set will kind of ask you to suffer through. But the good news is that once I've kind of recognized that I'm an Sn1 E1 pathway, I can get to my most important intermediate. So let's do that. Right? I'm waiting around, and so eventually, someday, somewhere, that tosylate group is just going to pop right off, and then you'll notice what I've formed is this tertiary carbocation, and then I'm going to draw it in a way that makes my life a little bit easier here, where what you'll see is there's my tertiary carbocation, my tosylate's in there somewhere doing whatever it's doing. And what you'll notice here is I kind of like put in what, wedges and dashes. So eventually we're going to be talking about the fact that the Sn1 E1 pathway is something that doesn't preserve stereochemistry. And then the Sn2 E2 pathways do have stereochemical consequences, right? And the reason for that is this asymmetric, well, I mean, it would have been, it's a bad example because it has no stereochemical consequences regardless of reaction, right? But if you would imagine that each one of these CH3s was a different group, now I've got something that's completely asymmetric, right? So even if this thing would have started chiral, the fact that I go through this like perfectly symmetric type intermediate here means that it's going to scramble whatever kind of stereochemistry is possible here. So that's a future video lecture, but just something important to recognize. So what's going to happen? Well, now we need to find a lone pair of electrons at least that wants to react with this positive charge. And really the only thing that's available is this solvent, right? This is really just bathing in H2O right now. So here's an example of where solvent is important, right? And in fact, this is sometimes called a solvolysis. This type of reaction pathway, E1-SN1, is also known as a solvolysis because the solvent has an opportunity to actually do something interesting. So your H2O is actually over here hanging out. Good old Mickey Mouse. That H2O is going to reach in, and if we cared about stereochemistry, it could reach in either way, right? It doesn't really matter in this guy. And so what I'm doing is I'm taking this thing down the Sn1 pathway. Right? I'm not done yet, but this kind of pathway where the nucleophile directly attacks the carbocation is going to put us in a substitution land. And so what you'll eventually have form is your substitution product. I might as well just include stereochemistry since I already started. Or include wedges and dashes, I guess I should say. But you'll notice is that this is not the product just yet, right? And this is another commonality to this pathway, is that there are a couple of steps that have to occur after the rate limiting step, which is the leaving of that leaving group. And so how are we going to get this thing to a neutrally charged product? Well, that's where water is just going to come in and remove an H. And so what we end up with is this alcohol. So there is the substitution, right? So in fact, we didn't necessarily just straight up substitute water, we substituted OH, right? And so we ended up with an alcohol as a result. Of course, that particular pathway is not the only thing that could happen, and this starts to get really, really messy. Instead of having that water attack there, I'm going to do this in blue, and I have to highlight a couple of things here. So let's say I just pick out one of these methyl groups and I look at H. Well, it turns out water could have just as easily ended up doing a base kind of reaction here, right? It's not a very strong base, but it doesn't really matter because it's at such a high potential energy state here. In which case I could have done something like that. And of course I would have ended up with my elimination products, right? So this is my E1 pathway. And of course, as we learn, As we learned before with like Zaitsev products and things like that, the more substituted version will be more likely. But in this case, I purposely chose one that wasn't that substituted, so I didn't have to consider that. But I could have just as easily taken that proton off. I could have taken that proton off. Whichever one was more substituted would be more likely. And so we would have ended up with a mixture of products. And even worse than that, when we get to the stereochemistry side of things, you'll get a scrambling of stereochemical consequences here, where you'll end up, if there's a chance for getting cis and trans in any of those elimination products, you'll get cis and trans product distribution. So it's an incredibly messy thing, and that's of course not even considering a substance that could undergo like a hydride shift or an alkyl shift. And so typically where you're going to see these kinds of reactions are idiot organic teachers like me will choose them as like a mechanism on an exam or something like that, right? Because you would never, if you had half a brain in your head, do this with a product that you, or a starting material you really cared about, right? But it's a really great kind of test of like the connections between mechanism and rate and the arrows we show and product distributions and stuff like that. So yeah, so let's kind of leave it at that. Everything else I think that you could probably figure out in your homework and such. The only other thing that I wanted to mention about these products right here, it turns out that temperature does have a little bit of a way to select between these. And as I said, we'll talk about this more in the very next video lecture, but I wanted to at least mention it here so I could get your brain thinking about it. It turns out that let's write it in blue, right? So E1s, or actually E2s as well, if we're in the other pathway, tends to be favored in high T conditions, right? In other words, high temperatures. And of course, that's relative to a lot of other things. But I think like if you're, if you're like putting your hand in the reaction, I don't know why you do that, and you're like, oh, that's kind of warm, right? Usually these elimination products are going to be favored at high T, whereas these substitution type products, again, this is true of SN2s and the other pathway, these are going to be favored at low T, right? And so if you imagine looking at that reaction and you kind of dip your finger in it, imagine that you're doing that, and you kind of say like, oh, that's kind of like, that's kind of nice, or it's lukewarm, assuming the acid or whatever's in there doesn't eat your hand away. Or if you put your finger in there and it's kind of like, ooh, that's kind of cold, right? That's where we're going to start to kind of press on the gas pedal for substitution type reactions. So a couple of other things to think about. Lots of mechanistic consequences here. If you have questions, I know a guy.